All right, so now we are official, folks. Okay, so let's talk about proofs then. So the first kind of a proof that we're going to talk about is proof by contradiction. Now, if you cannot read my handwriting, please let me know. I try to make it legible. So here is an example of a proof by contradiction. So just let's talk about an example here. Okay. So let's say in my example, I'm going to say assume if n squared is even. Okay, if n squared is even, then n is odd. The number n must be odd. Okay, so if I want to prove this by contradiction, then maybe I should have started by this. The problem is really this. If n squared is even, comma, then n is even. So this is what we want to prove. So if a square of a number is even, then the number is even. It has to be even. Now, based on proof by contradiction, what we need to do is this. We're going to say, okay, suppose this is how the proof by contradiction goes. We say if statement P is correct, then then we arrive at not P, that P is not correct. In other words, we arrive at a contradiction. So here's how we're going to do this. So let's say n squared is even. Okay. So how are we going to do this? I'm going to say, suppose n squared is odd. Okay. N squared would be an odd squared. Now, odd numbers, usually we use like 2n, because remember, if n is any whole number, 2n would be even, right? So 2n plus 1 would be odd. Okay, and if I square an odd number, what am I going to get? Well, I can square the binomial here, right? So what are we going to get? We're going to get 4n squared plus 4n plus 1. Now, 4 times any number, that makes it even. So 4n squared plus 4n, this is going to be even. An even number plus 1 is going to be equal to an odd number, correct? In other words, this is not even. Therefore, we have arrived at a contradiction. Odd number, and it is not even. Therefore, we have a contradiction. So the way the contradiction again works is that you say, okay, suppose, again, here we said if n squared is even, then n must be even. So we said we arrive at a contradiction. We said, well, what if n is an odd number? If n squared is even, so odd numbers squared, we just showed that it's not even. So that contradicts the premise here. And that would be proof by contradiction. The way the proof by contrapositive works, we're going to look at just 3 of them: contradiction, contrapositive, and induction. For contrapositive, here's how the structure of a contrapositive is that if statement P implies Q, okay, if P implies, the arrow is implication symbol here. If a statement P implies Q, then what is the contrapositive? The contrapositive of this statement is going to be if not Q, then that should result in not P. Okay, so for example, going back to if n squared is even, then n is even. So if n squared is even, we can think of that as a statement P. What follows then would be the consequence, right? So we're going to call that Q. So right now we have a structure if P, then Q, right? So to turn this into a contrapositive, that means if not Q. Well, not Q means if n is not even. Well, if n is not even, then n is odd, right? So here's the contrapositive of that statement that I made up. If n is odd, right? That would be the not Q. Q is even, N is even. So not Q would be N is odd. So if N is odd, then let's see, not P. N squared is even. So what would be opposite of that? Then N squared is not even, right? In other words, if it's not even, that means it is odd. So you see how the contrapositive works? You negate Q, you negate this statement, and then you negate this one. And then we need to show that if not Q, then that would result in not P. So if N is odd, so that means I have to start with that premise. If N is odd, that means N is 2K plus 1, where K is like a whole number. So let N equal 2K plus 1 be odd. See, we are allowed to make that assumption. We're given if N is odd. So I made N to be odd. Now we need to work on the then part. Then N squared is not even. Well, let's see. N squared is, that's going to be square of 2K plus 1, just like the one I had up here. And that's going to be what? It's going to be 4K squared plus 4K plus 1. And we just showed that this expression will definitely be odd, right? And that's what we just showed here. So if N is odd, then N squared is not even. And we just showed that. So we have proved this by contrapositive. Okay, so that's the structure of a contrapositive. Is everyone okay so far on that example? Any questions, anyone?
Does that say in the parentheses on the last one on the right side, it is odd, or is it
This
if
one,
it's odd? No, a little
this
bit higher.
here?
Yeah, that
Yeah, this is odd.
it
Yeah,
is odd.
yeah,
No,
it
no, it
is.
says it is odd. Okay,
Yeah,
sounds good.
if, see, not P, remember P said N squared is even, so not P, that means it's got to be odd. It is not even, so that means it has to be odd. Because we're talking about positive integers. Is everyone okay on this example? All right. If you have questions again, please ask. All right. Now let's look at the next proof. This next one is proof by induction. Then you may have seen this proof in a pre-calculus course. Maybe depends on the instructor and how far they get. But here's how this is proof by induction is going to go. The proof by induction works nicely for integers. But again, we will have application to linear algebra, as you will see later on. It works with matrices as well. So here's what we want to do, an example. Let's say we want to prove, and let me put star by these. Those are the proof types. So example, let's say we want to prove the following statement P, that if you add positive integers, 1, 2, 3, plus dot, 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 plus n, the sum of these is going to be n plus 1 over 2. Okay, suppose we want to prove this by induction. Now, you may have seen this statement, by the way, in Calc 1, when they talked about the Riemann sum. Something in Calc 1, they say like sigma k is going to be n plus 1 over 2. So you may have seen this already. There you go. This would be from Calc 1. But we want to prove this statement by induction. So here's how the proof by induction works. It has two parts to it. So the part one of the proof is this.
That's right.
P sub 1. That means the statement when n is 1. The value of n is 1.
Prove.
So if the value of n is 1, then the left side, the way this works, you just pick up one term. The first number 1 is all you pick up. For P1, you only pick one term on the left. Now, on the right side, we have a formula. N is 1. So I'm going to go 1 times 1 plus 1 divided by 2. And the right side is 1 times 2 divided by 2 or 1, and it checks. You see that the left side is equal to the right side. Okay, so the statement seems to be working for when n is 1. Now let's try it for when n is 2. P2 means when n is 2. So for P2, now I'm going to pick up 2 terms on the left side. So it's going to be 1 plus 2. Okay, for P2, you pick 2 terms. P3, you pick 1, 2, 3, and so on. So we want to see if this is equal to the right side, the formula on the right side. Now remember, n is 2 now. So I'm going to go 2 times 2 plus 1 divided by 2, and that's going to make it 3, and clearly 3 is equal to 3. So it looks like this checks also. True? Therefore, you could go on for P3, 4, and so on, but it's not necessary because it's going to work. Usually, we just show this for the first couple, and then we generalize. So here's what the takeaway from this part 1 is. We're going to say, we're going to assume that P sub K is true. In other words, what I have done is going to work for up to k terms. That is, i.e., the sum 1 plus 2 plus 3 plus ... plus up to the kth term is going to equal k plus 1 over 2. So we're going to make that assumption that this is true. Now, if this is true, then in part 2, we need to show that the statement is true for k plus first term. That p sub k plus 1 is also true. So in other words, this is going to work up to 1,000,000 when n is 1,000,000. 1,000,000 terms I'm adding. Is it going to work for the 1,000,000 and the first term, the next term? That's what this p sub k plus 1 is. Now, what we make the assumption about here, excuse me, the statement assume p sub k is true. This statement is called the induction hypothesis. So this is our induction hypothesis. Okay, now we're going to use this in showing p sub k plus 1 is true. So what does p sub k plus 1 now looks like? Well, p sub k, remember p sub k picks up k numbers, right? So p sub k plus 1 has k terms plus 1 more, so it has k plus 1 terms, right? So p sub k plus 1, therefore, is 1 plus 2 plus 3 plus ... plus k. Again, that's p sub k. And the next term is going to be k plus first term. So we need to show that the formula works for this. Now, the formula that you see up here, n plus 1 over 2, when you change this for k plus 1 terms in the series, this is going to become k plus 1. See the n here? Turns into k plus 1. This n turns into k plus 1. And then plus 1 that's already there makes it k plus 2 divided by 2. This is what we need to show. We need to show that this will work. Okay, so here's how the next step's going to go. So I'm gonna move this paper. Let me just slide it up here. Okay, so you can still see that part. All right, let's see if we can show this now. Because we can assume the induction hypothesis is true. Based on that assumption, I'm going to replace 1, 2, 3, all these add-ins up to k. I'm going to replace all of these, this sum, with the sum that the induction hypothesis gives us. So the left side, LS, the left side, therefore, is k times k plus 1 over 2. That picks up all of these, plus k plus 1, right? Plus that k plus first term. Will this equal to the right side? The right side should become k plus 1, k plus 2 over 2. So my task is now to show the left and the right side are equal. So let's work on the left side. On the left side, I'm going to actually get LCD and combine these two expressions. I have a fraction and I have a non-fraction. I'm going to combine them. So this is going to be k plus 1, common denominator 2. You can multiply the top and the bottom of this expression, k plus 1. Multiply by 2, divide by 2, right? So this is going to become 2 times k plus 1 divided by 2. And again, just this portion that you're looking at, isn't that just k plus 1? Once you divide out the 2's, so I haven't changed this. Now, I'm still working on the left side. The left side, I'm going to factor now the GCF from the numerator. See the k plus 1, k plus 1. I'm going to factor that. So once I factor k plus 1, then this becomes k. And I have a 2 from this expression. Once I remove the GCF, I have a 2. So that's k plus 2 divided by 2. Now look at the right side. This is equal to the right side, this being the right side. So we just showed that this statement actually holds for all natural numbers, for all positive integers. And this is how the proof by induction works out. Any questions, ladies and gentlemen, about the proof by induction? Is everyone okay on this work? Any questions about any steps? No? We're good?
Yeah.
Okay. And again, please, if you have questions, ask questions, and let me not lose sight of our chat. Okay, yeah, so thank you. Looks like everybody's okay then. Perfect. Remember, I apologize if I don't respond to your chat right away because I don't see it while I'm working. All right, so there you go. This is proof by induction. We will be doing these proofs, these 3 types of proofs in our exercises that we do later on. So for now, though, it's good enough for us to move on. And I'm going to now switch. Let me stop my share here with this one, and I'm going to change and share something else with you. I'm going to actually share the book with you now. All right, so hopefully, again, everybody now can see this is a page of the book. So in here, there you go. This is just the cover page of the book that we are using, by the way. It's Linear Algebra by Ron Larson and 7th edition of the book. This table of contents, resources, and here you go. We're going to start in chapter 1. Now, chapter 1 has 3 sections. And let me enlarge this. And keep in mind, since we are recording this, so if I go a little fast, I try not to, by the way. If I'm going fast, folks, please don't be bashful. Just tell me to slow down or just tell me, can you go a little slower or can you explain something again because I didn't get it? Because unless you tell me, I really would not know. But I'll do my best not to go fast. If I go fast, sometimes it's because it's like basic algebra stuff that you know how to do already. So I tend to go over those a little faster. Okay, so here's what we're gonna do then. This is a page of the book. We are in chapter 1. 3 sections. Tonight, I'll be happy when we get through sections 1 and 2, and we'll look at the applications next week. Now, again, since we are recording, I tend to show you the main topics so I don't have to write it and then you have to write it, and that just takes time. I much rather spend that time writing something that's in the book by showing you what's in the book, and then in return, maybe do more examples in the exercises, if that's okay with everyone. So we're looking at systems of linear equations. Now, this part of the course, by the way, I'm sure all of you have seen and worked with systems of linear equations, which is a good thing. So you're in familiar territories. Like, yeah, I've seen it. I know what we're doing here. And that's exactly what it is. So let's first of all look at the definition here. So this is the definition of a linear equation in n variables. Now, one thing on the notation here, in the algebra classes, usually we use x, y, z, and so on. So for now, in this book though, and this is a very common practice, by the way, instead of using x, y, z's, we still do that later. But for now, we're just changing those variables to x sub 1, x sub 2, x sub 3, and so on. So each x subscripted is a variable here. So this is a linear equation. And the reason it's called linear is because you simply have x. Okay, so there are not allowed to be any products. So I cannot have x1 times x2. That's no longer linear. I cannot have a square root of x sub 3, for example. I cannot have like sine of x sub 3. I cannot have exponents. It really has to look just like you're looking at it. The a's here, a sub 1, a sub 2, a sub 3. These are called coefficients. Remember, coefficients are the numbers that multiply by the variable. So that's what these are. These are the coefficients. The coefficients are real numbers. And the constant term is on the right side. Okay. On the right side is just b. B is simply a constant. The constant could be any real number, including 0, by the way. Okay, it could be anything. All the a's are real numbers. So that means some of those, not all of them, could be 0. So I could have a sub 1, 0, and a sub 2, a sub 3. All I need is just one term not being coefficient, not being 0. And there you have it. The a sub 1 here, this coefficient on x sub 1, it's called the leading coefficient. The leading coefficient because it's the first coefficient in that statement. Okay, so we have the leading coefficient, and x sub 1 is the leading variable. Together, they make up the leading term of the equation. Okay, so that's just some terminologies here. And then we'll do our own examples. But for instance, now look at, for instance, this one, example B. Look at this one. This is a linear equation because you have the variable, instead of x1, x2, x3, he's using just x, y, and z. The coefficients don't matter. The constant don't matter. It could be square root of 2. This could be pi. The coefficients are any real numbers. Okay, now here, remember I said we are not allowed to have like sine x, and we're not. C is also linear because x, see x sub 1, that's just x. There's no sine x here. Sine pi, that's a real number. It's a coefficient. Coefficients can be anything. So this is perfectly fine. The b on the right side in this example is e squared. And that's an irrational number. It's not a variable, right? Remember e, the base of the natural log? That's what that is. Therefore, that all A, B, C, the first part, are linear. Now look at the ones that are not linear. These are not linear. Why? Why is A not linear? Can anyone tell me? This one is not a linear
Because
equation.
they're multiplying two variables.
Very good. You got product of two variables, makes it nonlinear. How about B is not linear? Why?
There's a exponent variable.
Perfect.
We don't know where it
Exactly.
is.
Very good. Very good. E to the x. Remember, x has to be by itself. Now, and this one is not because.
It has a sign with the variable being the
Perfect. Thank you, Ariana. Exactly. So you have sign of a variable, not the variable. Look at C above and look at C below. You see, both of them have sign, but X is the variable. It's no sign X. Here, you actually have sign of a variable. So there you go. So hopefully we can now distinguish linear from
Can you
nonlinear.
explain sign of the variable one more time? Because I'm just a bit confused.
Sure, sure. So again, up here, I'm looking at C above, this C right up here, this one. Notice you have just the variable x sub 1, right? Its coefficient, it doesn't matter, sine, cosine, e, anything, any real number is fine. As long as you just have a variable by itself, it's okay. Now, if you look at this one, you have sign of a variable. You don't have sign of a constant. So here, sign is not a coefficient. You have a function, a sign function, not a coefficient. So for coefficients, it's okay to be anything as long as the variable is just x, y, z. X, Y, Z. So in here, again, the trouble is that I have a function of X, not just X sub 1. Is that okay with everyone?
So in a sense, it's kind of considered a constant because it's the fun x isn't. I mean, it's the sine function of x.
Right, it's not a constant. No, it is a variable. X is a variable here. So this is actually a function, sine function. Up here, you have just X. In any one of these, like A, that's 3x. Variable is just x. And then you have y. Variable is just y. Down here, variable z. Of course, we're not allowed to have product of variables. So in part C here, again, we have a function of x, not just x. So this sign, if they want to make this linear, they have to make this sign look like something up here. It could be like sine of 30 degrees, sine of an angle, that's fine, times separately, times x sub 1. Then it would be permissible.
Makes sense. Thank you.
Okay, everyone again clear on that? The linear versus nonlinear ones. All right, now, and then we look at what do we mean by solutions? The solution set is actually the set of all the numbers that work in all equations. So for example, here's a linear equation with n variables. And if I have n solutions right in here, there are n solutions. If these S's, S sub 1 means solution, solution 1, S sub 2 solution for X sub 2, S sub 3 is solution for third variable, and so on. So if you plug those solutions into the equation, we should get a true statement. The left and the right side should be equal. Then these make up the solution sets. The entire set of solutions is called solution set. That's what this is. All possible solutions make up the solution set. Now, sometimes we may have more variables than equations. So for instance, look at this one. And I'll give you an example myself too in a moment. Now, when you have more equations than variables, such as example 2, this equation I cannot solve uniquely. because if I have two unknowns, two variables, I need to have two independent equations so I can solve them. Well, here I don't. So that means I cannot solve and find a unique solution here. So the cases where there are more unknowns than equation, then we need to find the parametric solution set. So how does this parametric solution set works? Let me give you an example. You see the example here, but let me stop share here and actually share my this one. Hold on. I'm going to share there my OkioCam. Okay, so I'm going to show you an example of now what you call it, parametric solutions here. So in this example, let's say in my example here, I have 2x1 minus x2 equals 7. Again, because there are two unknowns, one equation, I cannot find a unique solution. So here's what I'm going to do. I have a choice to solve for either x sub 1 or x sub 2. So I'm going to solve for x sub 2 here. It's a little easier. I get 7. So move x sub 2 to the other side, bring 7 over. So this becomes negative 7 plus 2x1, right? That's what x sub 2 is. Okay. Now, at this point, I can declare x sub 1 to be any variable. Okay, so I'm going to let x sub 1 be t. T is a general solution here. Okay, they call it a parametric solution. So I'm going to let the parameter represent the solution, t. And t could be any number you want it to be. So I'm going to say t 5,000. That's fine. It works. Somebody else says, I want t to be 500. That would also work. There is no unique solution to this one. So once you determine x sub 1 to be t, and by the way, we call that x sub 1. X sub 1, they call it a free variable. It's a free variable. Okay. Now, x sub 1 is t, so x sub 2 is going to be negative 7 plus 2t. And that would be the solution for x sub 2. Now, what would be a particular solution? This is when you choose now. I personally want to let t to be 0. I like 0. So my choice of t0, x sub 1, will be 0. And what will x sub 2 be? X sub 2 would be 2 times 0, 0, and then minus 7 makes it negative 7. And there you go. So a solution is 0, negative 7 for this equation. If you want, you say, you know what? I like t to be 1. And that's my favorite number. Okay, for that choice, then x sub 1 is going to be 1 because x sub 1 is exactly t. And x sub 2 is going to be negative 7 plus 2 times t. So it's going to be negative 7 plus 2 or negative 5. So here is yet another solution, 1 and negative 5. You see how that works? And these are called particular solutions. See, specific, a very particular solution. I have 2 of them. Now, in this parametrization, x sub 2 depends on x sub 1, right? X sub 2 depends on x sub 1 because I solve for x sub 2 in terms of x sub 1 right here. True? Now, there is no rule on what you can let the free variable be. Excuse me. So if you want, you can say, well, I would like to let x sub 2 to be t. I want my free variable to be x sub 2. Okay, well, if you let x sub 2 to be your free variable, then now I need to solve for x sub 1 in terms of x sub 2. I'm going back to here, the very original equation. Let's solve for x sub 1. Well, x sub 1, remember 2x sub 1 is going to equal to 7 plus x sub 2. I'm moving negative x sub 2 to the right side. And then divide both sides by 2. So I get, to divide by 2 is to multiply by a half. And there you go. See, I solved for x sub 1 in terms of x sub 2 because I want x sub 2 to be my free variable. Now, this time, I let t to be 2. Again, you can let it be 0, 1, 2, whatever. I'm going to let t to be 2. Okay, remember x sub 2 is t. So in other words, this is going to be 1/2, 7 plus t. Plug in a 2 in for t, and I get x sub 1 is half, 7 plus 2, and that's 9/2. So another solution here is x sub 1, and x sub 2 is t. My t is 2. It's going to be 2. There is another solution. Now, this time, just to show you, I'm gonna let t to be -5, and you'll see why. I like -5. Let's plug it in. What is x sub 1 gonna be? X sub 1 is gonna be 1/2, 7 plus t, and that's gonna be a half. 7 minus 5 is 2, and that is 1. So here's another solution. Remember, t is x sub 2. So my solution is x sub 1, 1, and x sub 2. We always write these in alphabetic order or in increasing order. So the solution is going to be an ordered pair, x sub 1 followed by x sub 2. And you can see the reason I picked that to be is because I can get the same exact solution. So it does not make a difference how we choose the free variable in equations like these, where you have more unknowns than you have, more variables than you have equations. So is everyone okay on the work that we just did? Are we good?
I have a question.
Yes, ma'am.
So before in the textbook, we were talking about the parametric solutions, and the points of the like 0, -7. Is that one of the parametric solutions?
Oh, this is actually a solution. The parametric part, I'm glad you asked. This is the parametric one. I'm going to write both of them. The parametric solution, x1 is t, x2 is -7 plus 2t. There you go. This is what's called a parametric solution. So parametric solution is the general equation. If I choose my free variable to be x2, then here is how this works. X sub 2 is t, x sub 1 is 1/2, 7 plus t. This is another parametric solution. Depending on, see here, my free variable is x sub 2 versus x sub 1. So both of these are called parametric solutions. These have infinitely many solutions inside of them. Then 1, -5, 0, -7, these are, or 9/2, comma 2. These are particular solutions, specific. They call them particular solutions. And there you go. So that's what these are. So the parametric, again, to answer your question, Ariana, is this one. These are the parametric solutions. Your parametric solution will have t in it. In general, t can be any real number.
Perfect. Thank you.
You're very welcome. Is everyone okay on this work? Very good. Okay. Fantastic. So let me now stop this share. I'm going to go back and share the book with you again. And this is where we were. Okay, so that's what the parametric solutions are. So if you look at the example, for instance, that's in the book, now this one makes sense. There you go. Here's the parametric solutions. You see that? I'm sorry, I picked so many of them. There you go. That's going to be parametric solutions right here. ST doesn't matter. These are dummy variables. Up here, he has parametric solutions like that. Remember, your parametric solution has T in it for x sub 1, x sub 2, x sub 3, and so on. Once you plug in a number for T, then you get a specific, a particular solution for that system, for that equation. Okay. Great. Now let's extend what we just did now to a system of linear equations. So now that we have the notation for one linear equation, well, if we make a whole bunch of these now, we have a system. So the fact that you have two or more equations creates the system. So now I have a system of equations. This one, let's see, the subscript A sub 1, 1. The first letter is like the row, the second letter is the column. So A sub 1, 1, I know it looks like 11, 21, 31, but these are actually subscripts for row and columns. And up here, he mentions it, a system M equations, N variables is written this way. So A sub 1, 1, that means the first row and the first column, if you will, of the system. A sub M, letter M, this one, A sub M, that means this is the coefficient on the first variable in the mth, for the mth equation. So this is what the system now looks like. The right side, these B sub 1, B sub 2, 3, and all the way down to B sub M, these are just the constants. Okay. Now again, the solution is any set of numbers that work this time in every equation, not just the first one, not just the second equation, not just the third. They have to work in each and every one of them. Then that's called a solution to the system. Now, if the system has a solution, the system is said to be consistent. Let me skip these for now. Okay. Let me stop here. So, in the way of naming the systems, by the way, folks, if there is at least one solution to the system, we call the system consistent. So consistent systems have at least one solution. If the system does not have a solution, we call those inconsistent systems. So inconsistent systems have no solutions. And there you have it. So exactly one solution, the system is consistent. The system has no solution. Number 3 is called inconsistent. Now, the consistency requirement, by the way, see both number 1 and 2, we have consistent. The condition is to have at least one solution. Number 1 says exactly one, that's fine. Number 2, infinitely many means more than one. So as long as there is at least between number 1 and 2, as long as there is at least one solution, the system is consistent. Now, ideally, we would like to work with case number 1. We would like to have unique solutions, only one solution. Not having a solution, of course, is not good. Having too many solutions is not good either. right? So number two, a system actually that has infinitely many. We go as far as calling it a dependent system. So it's not only consistent, but it's dependent. So dependent systems have infinitely many solutions to them. So that's just the terminology as far as the number of solutions to the system. Everyone okay so far on this? Now, okay, thank you. Now, let's take a look at it. So what you're looking at here in this figure, this is good. You've probably seen something like this before. Here, you have a visual of a system in part A of two equation, two unknowns. There, right below it, it gives you the two equation and two unknowns. Now, because this is a two-dimensional figure, because you have two variables, I can draw it graphically. And the point of intersection of the two lines is going to be the solution. So this is an example of a system that is consistent and has exactly one solution. The case where you have two coinciding lines, you have one line overlay on top of the other. These equations are really the same. X plus y equal 3 is the same as the one below it. It looks like the one below it, everything was multiplied by 2, wasn't it? 2x, 2y, 2 times 3. So it's really the same line. This is a consistent system. And this one is the one that has infinitely many solutions. So that's an example of a dependent system. And the part C is the last one here, where we have two parallel lines. So here's a case where we have two parallel lines. And remember, parallel lines never cross. So we never get into a figure A situation. Therefore, because there is no point of intersection, hence their system is inconsistent, meaning there's no solution to this one. I cannot find an ordered pair that works in both of them. Remember, the solution must work in every equation. So there you have that one. Now, how are we going to solve the system of equations? Okay. I'll show you one. This is just kind of how it's going to turn out. If you look at on this screen, so here we have a system of three equations and three unknowns. Once we reduce the system, you see how this looks like now? Look at this. It doesn't have, like the second equation now, got rid of the x, don't have the x. Look at the third equation, does not have x or y in it. So this is how we would like to reduce, they call it. We're going to reduce the system from left to right. How are we going to do this? You're going to see it in a moment. So the system that's on the right side, it has this stair-step formation. See, you go below x, move over, below y, move over to z, like staircase. Well, this system is said to be in its row echelon form. Now, the echelon is a stair step right in here. See the stair step pattern that you see. So the system on the left is the general system. The one on the right is row echelon form. Now, we can solve this system using what they call back substitution. And again, we will do that ourselves. I'll show you how. Once you have a row echelon form, the next step is to do a back substitution, and that will solve the system. See, to solve a system. So the back substitution, when we get done, actually solves the system. So let's see. I want to see if he shows you the steps. He's just showing how the back substitution, it's really simple too, by the way. The back substitution is just that. You start with the last equation. You then back substitute for 2 for z in the second equation. So you're going back substitution. When you back substitute, that's what he's done here. You see that? Plugs in a 2 in for z. and you get y to be -1. Once you know the value of z and y, you back substitute into the first equation. Now you know what y is, and you know what z is, right? The value of those. So we back substitute, and then you solve, and here's the solution to the system. Okay, once you have in echelon form, the back substitution is really easy, folks. It won't take much to do this. Now, the two systems, by the way, that we see up here, these systems, these are called equivalent systems. What that means is that they may look different, and they do. Look at the second equation here, look at second one, look at third, look at third. They look different. Although they look different, but the solution hasn't changed. So they share the same exact solution. So when that's the case, we say the systems are equivalent systems. Same solution, but they may look different. Okay. And it's okay to work with equivalent systems. Now, what operation are we allowed on systems? So that's what this number 1, 2, 3 are next. These are operations that will result in systems to look different, but nonetheless, they're all equivalent, means they have the same solution. So there are 3 basic rules here. Rule number 1 allows you to exchange or interchange 2 equations. And that makes sense. For example, look at example 7. If instead of writing the first equation, the way the system looks, had he written the bottom equation, had he written this equation, the bottom one first, and the top one, moved it to the bottom, that wouldn't change the system's solution, right? It will look different, but it doesn't change the solution. So that's what rule number 1 allows us to do. It says if you need to, you can swap rows. You can swap equations. That's fine. Rule number 2 is the multiplication rule of equations. It allows you to multiply an equation by any constant, so long as you don't multiply by 0. Okay, so that's rule number 2. So far, we have 2 rules then for producing equivalent systems. Now, rule number 3. Rule number 3 allows us to add a constant multiple of an equation to another equation. So if you wanted to, for instance, I can multiply this entire equation, first one, by 2, by 4, by 5, by anything. And then add it to the third equation if I wanted to, or to the second, doesn't matter, and add it to that one, and that will become a new equation. This rule allows us to do that. Okay, so these are called elementary operations that produce equivalent systems. Now, we're hoping that we can use these elementary operations to get the system, such as this one in number 7, to look like this one, the echelon form of the system. You see that one? That's what we're hoping to accomplish. And as far as the visual goes, by the way, when we have 3 variables, because these are linear equations, so the graph of any one of these is going to be a flat surface, as you see. There you go. So that's what this first equation is. So he's actually graphed these surfaces in 3 dimensions. And this one has a common point of intersection right there of the 3 planes. And that's what that is. Okay. Is everyone good, by the way, so far? Any questions, anyone?
No.
Okay. Since you're okay, let's continue on now. Let's see what else. Oh, how do we know if a system, so if a system is consistent, has a solution, you just saw Nothing bad happens. You get the echelon form, you can do back substitution, and there is a solution. So here's a case where the system has a unique solution. Now, what if the system is inconsistent? What would be the sign of an inconsistent system? Well, when you try to turn the system and rewrite it as an equivalent system in echelon form, what happens is that you end up getting something like you're looking at here. You see down here the equation 0 equals -2. As you go through those three procedures above of elementary operations, we're going to get some statement that doesn't make sense. 0, of course, does not equal to -2. So anytime we get a statement that looks like this, that is the sign of a system, that is inconsistent. So, and here's the visual on the three surfaces he's graphed. There is no common point of intersection between the three. So that would be, again, the visual. And don't worry, you're not responsible for graphing these surfaces, by the way. But if you work with Desmos, something I'm sure most of you know about Desmos, Desmos has also a 3D version. If you go to desmos.com/3D, D as in David, as in 3D, 3D, you can actually graph these surfaces now in Desmos, and it's really cool. You can see how these turn out. Okay, so we saw the case where there is a solution, single solution, no solution. Now, what if there are infinitely many solutions? How do we come across those? So here's now a system again. He goes through, and I'll do example where we go through and do this ourselves. But once we go through, again, towards row echelon form, look at it here now. We end up with an equation that has no variables, but this statement is a true statement. 0 is equal to 0, because that is a true statement. This is the sign the system is dependent. And look now, we actually have, instead of 3 equations, now we have 2 equations down here, right? Here's one equation, and here's the other equation. The third one is gone. That just shows the dependency of the equations. It means you have a redundant equation. This third equation, when I see 0 equals 0, that means that third equation was a linear combination of the first 2. I could have written or rewritten equation number 3. This one in the beginning, this one right here. This could have been written as a linear combination of the first and the second equation. That's what that means. And that's what he does it right in here. See, equation, the third equation, it says is unnecessary, and because it's gone. We don't need it. So this is a sign of dependent system. Now, the solution to dependent systems, we always write the solutions because they have infinitely many solutions. And the solutions are going to be parametric solutions for these. If you look, you have 2 equations, but 3 unknowns. When the number of unknowns exceeds the number of equations, the solution will be parametric. Okay? And that's why he has them in this form. And usually, by the way, remember I said your free variable, quote unquote free, he chooses them to be, and usually it's not him, Larson, it's a convention. Usually you let the last variable, remember I have x sub 1, x sub 2, x sub 3. You let the last one be your free variable. It's not wrong if you let the first one, x sub 1, to be free variable. If you want x sub 1 to be free variable, now you got to solve x sub 3 and x sub 2 in terms of x sub 1. But this is how it's done in every linear algebra textbook. You let the last variable be your free variable by convention. And then if you look at the second equation, x sub 2 minus x sub 3 equals 0. Doesn't that mean x sub 2 equal x sub 3? And if x sub 3 is free variable, call it t, then x sub 2 is going to be exactly x sub 3, which is t. That's also t. But it's like, how do you know he didn't let x sub 2 to be t? I know he didn't, because he's written x sub 3 first. You always work from the last variable and then work backwards towards the other ones. All right, and there we have that one. Oh, good, and we have reached these exercises. Now, I'll do a couple of exercises, and let's see, how are we doing on time? It's 8:25. And how is everyone doing, by the way? Are you all okay? I know it's kind of late.
Yeah.
Hopefully you're hanging in there, right? Okay, fantastic. Thank God it's only once a week, right? If it's only once a week, it's tolerable. We can handle it. Okay, again, I know it's getting late and probably you're getting tired, but let's do some examples here of some of these exercises. We will work them, and then we call it the evening. Now, for these exercises, again, in section 1.1, so next week we'll do section 1.2 because we're doing exercises now. Let's try, and I just randomly pick these. I try to do problems that are similar to your homework problems. So when you do your homework problems, you have a point of reference. So having said that, let's take a look at exercise number 30, for instance, number 30, right down here. I believe you're doing something like number 29. So in exercise number 30 here, back substitution. The question reads, in these exercises, use back substitution to solve the system. So I'm going to switch now to, let me write it on my paper first before I point away from the screen into my OKIO cam. X sub 1 plus x sub 2, I'm just writing the system, folks. And x sub 2 equals 0. Okay, the question says use back substitution to solve the system. This shouldn't be bad, right? Let me stop share and then change share to my OKIO cam. All right, so now you can see. So here's exercise number 30, and we are in section 1.1. Now, back substitution, notice x sub 2 is 0, so it's already solved for x sub 2, correct? It's a 0. So what am I going to let my free variable be, by the way?
T? Oh, 0?
My free variable.
X sub 3.
X sub 3.
X sub 3. Very good. Excellent. Thank you, Leo. Also, yeah, x sub 3. So we're going to let x sub 3 equals t. Remember, usually you let the last variable to be your t. The fact that x sub 2 is 0, so be it. That's okay. Now, we actually put x sub 2 0 in here. That's never going to change, right? That doesn't depend on t. So our x sub 3 is t, our x sub 2 is 0, and now let's solve for x sub 1. Okay, in that first equation, we want to isolate x sub 1. So this is going to be x sub 1 equals, I'm going to move x sub 2, x sub 3 to the other side. So that's going to be negative x sub 2, negative x sub 3. And of course, x sub 2 is 0, x sub 3 is my free variable, right? That's our free variable t. So that's going to be negative t. Therefore, x sub 1 is negative t. The solution set is going to be in the form of x sub 1, x sub 2, and x sub 3 in parametric form. You see that? This has infinite solutions in it, doesn't it? And if you want, just pick randomly any number you want for t. The question didn't ask for it, but if you want, this is just me. I'm gonna let t to be 1,000. I like that number. So if t is 1,000, now I can give you a particular solution. There you go. You can let your own numbers be whatever you like them to be. So that's going to work out for everyone. Is everyone okay on this example?
Yep.
Fantastic. Now let's do another one. In this next one, again, let me stop share this one, and let's change my share to the book. There you go. For this next example, let's see. Oh, for like on the exam, by the way, folks, I'll never have questions like number 45, 46, nothing like this on the exams. The exams will be pretty much like the ones we're doing, where you have systems that are normal, integer numbers. Something like number 45, 46, by the way, wouldn't be bad, right? You just have to multiply everything by 100. But it will be more like, the ones that we're doing again. So let's take a look at in numbers 37 to 56 now. The question says, solve the system of equations. Okay, so now we want to solve the system. Let's take a look at how about we do a system of 3 equations, 3 variables. How about number 52? This one. Let's take a look at number 52, folks. Okay, again, I'm going to write the system. This is number 52. X sub 1, and then space plus 4x sub 3 equals 13. And then I have 4x1 negative 2x sub 2 plus x sub 3 equals 7. And lastly, I have 2x sub 1 negative 2x sub 2 negative 7x sub 3 equals negative 19. And there you go. Okay, so let's see how we're gonna do this. Let me stop share and go back to my OQCam. All right. So now I have the system here written down. Okay. Now let's see. What do you think we could do on this one?
Multiply the third equation by negative, so we can take away the x sub 2, so we can cancel that out.
Oh, okay, good. You want to eliminate x sub 2. Excellent. Sure. Now, so thank you. Yeah, we will do that. Thank you for that, Jesus. Remember the 3 rules we had for equivalent systems. We are allowed to switch equations, interchange them. We can multiply any row by any non-zero, and that's what multiplying by negative is, like multiply by -1 to be specific, and that is allowable. That's rule number 2. And rule number 3 allows us to multiply a row and add it to another row and replace that. I call it a row. It's really an equation. Later on, when we talk matrices, each equation will equivalent to a row of a matrix. So that's why I'm used to calling them rows and columns. Okay, well, let's do that then. So we're going to multiply this one by negative. So now I'm going to have negative 2x sub 1 plus 2x sub 2. I put the details, by the way, on these folks. I know some of you may just do it in your head, but I'd rather err on the safe side. just to make sure everybody's on board with what we're doing. So there you go. That's what we just did. Multiply third row by -1, and then add it to the second one. So that's going to make it 2x sub 1 plus, and please verify if I do make a mistake, and I'm sure I've made many mistakes before in the past. So feel free to correct me if you see something I do wrong. So this is what I get. 2x sub 1 plus x sub 3 equal 26. Now, we like to work with smaller numbers, right? So is it okay if I divide everything by 2 in this third equation on this one? Let's divide everything by 2. So that's rule number 2. I'm multiplying by 1/2, if you will. There you go. This is rule number 2. I'm allowed to multiply an equation by a non-zero constant. So this means x sub 1 plus 4x sub 3 is now equal 13. So the system is now x sub 1 plus 4x sub 3 equal 13, right? And then we replace the second row, second equation with x sub 1 plus 4x sub 3 equals 13. And the third equation is 2x sub 1 minus 2x sub 2, negative 7x sub 3 equals negative 19. Interesting. And so what do you think we should do next? And check out these two equations, by the way. Unless I made a mistake, they look the same, don't they?
Don't we, isn't that the same as 0 equals 0? So we can take one out?
Exactly. If you want, for example, the next step, I can say, why don't I multiply the first equation by -1, add it to second, and this gives you 0 equals 0. But they're the same, so there's no need writing it twice. So I'm going to actually write it as x sub 1 plus 4x sub 3 equal 13. And what do we have next? We have this one, and then we have negative 2x sub 1. And let me see. This one, the third one. I have 2x sub 1, negative 2x sub 2, negative 7x sub 3 equals negative 19. Sorry, negative 19. Okay. And good. So looks like now we have 2 equations, 3 unknowns, right? So this system is going to be dependent, isn't it? And we know it's dependent from right in here. See, those equations are the same. So that's the sign the system is dependent. Now, we need to decide on a free variable, right? Let's see. But before we do this, make sure, does everything look right, by the way, everyone? We have, yeah, this looks good. Now, in here, let's actually eliminate variable x sub 1, right? Let's eliminate x sub 1. How do I get rid of x sub 1 now?
Multiplying the upper equation by negative.
Thank you. Exactly. So we're going to multiply the first equation by -2. So that's going to be -2 x sub 1, -8 x sub 3 equals -26. Add it to the existing second equation, -2x2, -7x sub 3 equals -19. These add to 0, so I have -2x sub 2, -15x sub 3 equals to -45, correct? So now let's see how this is going to look like. Now, the first equation, let's see. Oh, okay. We can actually replace this second equation with this one. So here's what I'm going to write. Here's my first one, x sub 1 plus 4x sub 3 equals 13. And now this will be a new second equation. That is negative 2x up 2, negative 15x up 3 equals negative 45. True? And this system is in echelon form. Remember, the key is to get it in the echelon form. In echelon form, you have x sub 1 in the first equation. You don't have x sub 1 in the second one. So now the system is in echelon form. Is everyone okay with this so far?
I had a question.
Yes, Ariana.
When you replace one of the equations, which one do you pick to replace? Because you multiplied one by a number to
Right.
cross out the other one, so.
Sure. Again, because we want to get to the echelon form, right? Echelon form. So I was looking at this here. You could make this one, we could make it into a 0. And that's what we did by doing this operation. Turn this into a 0. So I have x sub 1 from above, and this will be gone, and I won't have it anymore. So the question is, how am I going to get rid of 2x sub 1? Well, negative 2 times that makes opposite. Opposites add to 0, and that's how I can get rid of this. So the focus is right in here. That's the deciding factor. Because I have x sub 1 directly above, I do not need an x sub 1 in the next equation. I got to make sure that's a 0. So whatever it takes to make that 0. And in this case, again, because I see 2x sub 1, so I need opposite of that, negative 2x sub 1. That comes from the equation above. So multiply the top by negative 2, add it to the second equation, replace the second equation. That would be rule number 3 of elementary operations on systems, for equivalent systems. Does that answer your question, Ariana?
Yeah, it does. Thank you.
Okay, you're very welcome. All right, is everybody good so far? Okay, so if you're fine, then once you're down to echelon form, now we can actually finish this in parametric form. What is the next step, folks? What should I do? Here's a hint.
Don't we
Use back substitution?
The back substitution, remember, I don't have a solution to back substitute. I'm glad you pointed that out. Here is how the back substitution would work. Just making something up. Equal to 2z equal 1. There you go. See, once you have a system in this form where you have solved for a variable, now you back substitute to solve for the second variable. And then you know both of these, you back substitute in here and in here to solve for x. So that to do a back substitution, it requires that we have solved for one of the variables and we have a number for it. For this one, again, because we have 1, 2, 3 unknowns and only 2 equations, so the system is dependent. The back substitution, we don't want to do a back substitution. We want to do is declare. What do we declare? Free
variable.
Free variable, exactly. Remember, the solution is going to be parametric. This is going to be a parametric. The back substitution works with these, but right now we just do a parametric solution. Question?
Just a question. Why couldn't we get rid of the x sub 3 if we were to make both 60 and remove the x sub 3?
Oh, see, x sub 3 actually has a value. I mean, how can you?
So 4 times 15 is 60, and 15 times 4 is 60.
Okay, so
And then we can multiply, either one can be negative. I mean,
okay, how, if you would please, Jesus, how are you going to get rid of x sub 3?
I would multiply the top term by 15.
Top equation by 15.
Yeah. And
And
then the bottom equation, I would multiply it by -4.
-4. Okay, when you do that, then we're going to get 15x1. Of course, the x's go away. x1 and see, hold on, whatever 15 times 13 is, this will give you 8x sub 2 gives you a number now, right? So for this one, see, we haven't solved it now. Okay, you're going to multiply the top by a number, bottom by a number. Then aren't you going to add them together? Right? Because we can't just multiply. We multiply and combine them, right? So I'm multiplying the top by 15, bottom by -4, no problem. And then we add the two equations together, and we're going to replace an equation. So let's say here's my first equation. And we're going to do what you suggested to do. So when we do that now, what do we get? 15x1. The x2 is going to be plus 8x sub 2. X sub 3s are going to go away. I'm multiplying by, yeah. And
In the same spot?
X sub 3s go away. And this is going to equal to whatever, this is the arithmetic, 15 times 13 plus 4 times 45 is, right? Isn't this what we're going to get?
Yeah, so it would be redundant.
Well, it really doesn't help us. See, I still have x1, x2, x3 in it. You see that? It doesn't solve it. You see that x sub 3 is still in the first equation. You were right. What you did was get rid of x sub 3. You did in the second equation. But see, in the first equation, you still have it. I still have 3 variables. So that doesn't really help me solve. Are you okay with this, Jesus?
Yeah, I'm okay. Thank
Yeah, again, the issue is right in here. Right now, let me write it nicer. I have x sub 1 plus 4x sub 3 equal 13. 15x sub 1 plus 8x sub 2 equal to, call this a number, whatever that number is. See, this is what I'm saying the issue is. I still have x sub 1, x sub 2, x sub 3. I haven't solved it. We just have another equivalent system.
So that's why it's called the echelon form.
Right, and this is not in the echelon form, by the way, is it? You see that?
No, because it's redundant.
Right, the echelon form is going to be like this: x sub 1, x sub 2. This is the echelon form. Everyone okay with this? You see how that works?
Yeah.
Okay, fantastic. So now going back to here, let me write it clean. So this is where we were. Let me, so I'm going to rewrite what we had. I had x sub 1 plus 4x sub 3 equal 13, and then -2x sub 2 plus 15, x sub 3 equals -45. Now,
Professor,
yes, ma'am.
I think someone asked a question in the chat.
Oh, thank you for that. Let me see. How do you decide which equation gets replaced after you add? Okay, to answer that again, the one that gives you the echelon form. There you go. This is my guide. Here's x sub 1, x sub 2. It's whatever it takes to eliminate. Look at the step prior to this. Before this, I have x sub 1, 2x sub 1. This is what Ariana was asking too. How do we make this, decide which one? So this needs to go away. The 2x sub 1 needs to go away. So I have the echelon, the staircase, the stair step pattern. So I need to do -2 times that. And the fact that I multiply by -2, everything multiplies by -2. And then it gives me the next equation. And the next equation now is in, again, I'm going to call this the echelon form. And there you have that one. So that's the deciding factor on that one. Okay. And let's see. Okay, and Warren says, okay, thank you. That makes sense. Okay, good. So have I answered everyone's concerns in the chat? Everybody's good? All right. So we're almost done with this, folks. Now, the last step here is to decide on our free variable, right? So what would you like to let the free variable be?
Would t be able to be the free variable?
Not t. Remember, the free variable is either x sub 1, x sub 2, or x sub 3. T is what you're going to let it be. So which of those you want me to make free variables? X sub 1, x sub 2, or x sub 3?
X sub 3.
X sub 3.
X sub 3, very good. Always the last one. Let's agree to that. So free variable x sub 3. And it really, what does that mean, free variable? That means it's free to take on any values. So then we say free variable is x sub 3. Look at the next step. See, x sub 3 is t. That's the solution to x sub 3. It is free to take on any real number. In that sense, is quote unquote free. It's free to assume any variable, any value you want it to, 0 to infinity, -5 billion, whatever you want it to be. But once x sub 3 free variable is decided, now x sub 2, x sub 1 will be stated in terms of x sub 3. So let's solve for x sub 2 in the second equation. -2x2 equals -15 x sub 3 minus 45. I simply moved 15 x sub 3 to the other side. That's what I got. And then let's divide throughout by -2. To divide by -2 is to multiply by -1/2. So it's going to be 15 halves x sub 3 plus 45 halves. True? That's what x sub 2 is. Our free variable x sub 3 is t. So that means x sub 2 is 15 halves t plus 45 halves. And there you have that one. And our first equation, we need to solve for x sub 1. X sub 1 is going to be 13 minus 4x sub 3. And now x sub 3 is our free variable. Remember, that just assumes anything you want it to. And therefore, x sub 1 is 13 minus 4t. So x sub 3 pretty much dictates our solutions here. If you want, for example, let t be 0, just the random. Remember, there are infinitely many solutions. So this is just one that I'm interested in. It makes it easy. If t is 0, so what is x sub 1 going to be? If t is 0, x sub 1 is going to be 13, isn't it?
Yeah.
What is x sub 2 going to be?
45/2.
Thank you, 45 halves. And x sub 3, of course, is our t, so that's just 0. And there you go. This is one particular solution to the system, one of infinitely many solutions. if you want, again, pick any number. Let's say we have 35 students. I could have 35 different answers at this point. But every one of those will stem from these three. You see that? So, what do you think, folks? Is this doable?
A lot of practice.
Sure, but it's systematic, right? Something that may be tedious but doable, I think.
I think it's because like from the previous maths, we're so used to just, I mean, like for example, seeing x sub 1 equal, I mean, x sub 2 equals 15 over 2 and t plus 45 over 2. And because of the previous maths, I feel like I have a tendency of wanting to substitute that wherever I see x sub 2.
All right.
Yeah, but I mean, yeah, it's just practice.
Sure. That makes sense, Jesus. Thank you for your input. Yeah, absolutely makes sense. But then again, for dependent systems, this is something that happens. The solutions are often given in parametric form. And then, now remember, we chose the free variable x sub 3. Somebody else says, you know what? I want x sub 1 to be my free variable. That's fine. So for them, if you want x sub 1 be free variable, x sub 1 is t. Now you write x sub 2 and x sub 3 in terms of x sub 1. And then you get your whole set of parametric equations or solutions. Ultimately, they all have the same set of solutions. It's just how you represent them.
I have a quick question, Professor.
Yes, sir.
So, because we were unable essentially to come up with a general solution, what we effectively did was we substituted a variable so we can come up with a particular solution?
That's correct.
Okay, perfect.
That is correct. And this will happen, by the way, folks, just so to keep it in check. This will happen anytime you have more variables than equations. See, I have 1, 2, 3 unknowns, don't I? 1, 2, 3. But I only have 2 equations. So anytime you have, again, more variables than equations, your solutions will all be parametric. Now, if I have more equation than variables, that's actually not a big deal. For example, suppose I have x plus y equals 7, x minus y equals 10, 2x plus 2y equal 14, 3x minus 3y equals 30. How many variables, unknowns, does this system have?
2.
2, right? 2 variables, x and y. And I have 1, 2, 3, 4 equations. Do I need 4 equations? No. So 2 of these are redundant. And in fact, it's this one. I multiply first one by 2. See that? So I don't need that. So it's okay to have more equations than variables. And when we do, usually they just get knocked out in the row echelon. If we were, and you can try this, if you try to do a row echelon of this system, you're going to get something like this. Let me actually, real quick, because we are almost done. Let me make that 8 so it works out nicer. I'm adding the 2 equations. So I get 2x is 18, x is 9, and put 9 here. 9 for x, and y would be -1, right? So if I do this system, notice I cross through the equation. If I didn't and I go to row echelon form of this, the system is going to look like this. It's going to look like this. X is 9, y is -1, 0 equals 0, 0 equals 0. That's what it's going to look like.
Would that be considered a particular solution or a general solution?
No, this is a general solution. This has only one solution, a unique solution. So yeah, the answer is 9, -1. Nothing else works.
So that means general solution?
Right. This is the general solution. There you go. And we gain nothing from the last two. Now, later on, and this could happen as early as next week, when we work these, you will see these systems and we will use like Symbol Lab and things like that to make this go faster, by the way, folks. Remember, only in chapter 1, we do this like by hand. After chapter 1, we do everything either using your calculator, if you're comfortable with your TIs, if you have them. If not, use Symbol Lab, the one I will show you. We use it. And then you get these really interesting looking matrices. Like, for example, the matrix for this is going to look like, I don't know, 1, 0, 9, 0, 1, -1, 0, 0, 0, 0, 0, 0. That's what this matrix is going to look for that system. But it's good that now we recognize what this means. Once we see a matrix like this, then we try to reflect it back to and see as a system. Okay, so this is what this means. That means I had two equations because I have rows of zeros. That means I have two equations that were redundant. They're not contributing anything to the solution. So that's what that is. The sign of that is. Good stuff, huh? Okay, so if it's okay, I'm going to stop the share.